There is a number waiting for you tonight that will genuinely unsettle you. One followed by 120 zeros. Not the size of the universe, not a count of atoms. It is how wrong physics is when it tries to weigh a box of nothing at all. Here is the part nobody tells you in school. Empty space is not empty. The vacuum between your fingers right now, the darkness between every star in the sky, is not a void. It seethes, it boils, silently and permanently, with energy that can never be switched off. We know this because we have measured it directly in real laboratories with real metal plates pulled together by the empty space between them. That is not theory. That is a photograph of nothing pushing back. So physicists did the obvious thing. They took our best theory of the very small quantum field theory, the same framework that predicts particle behavior to 12 decimal places of accuracy, and asked it a simple question. How much should empty space weigh? The answer it gave was so large, so violently disagreeing with what we actually observe in the night sky, that it is now known, without exaggeration, as the worst prediction in the history of science. Tonight, we are going to find out what nothing is actually made of, why it refuses to add up, and what that failure might be quietly trying to tell us about the universe. Get comfortable. Hit subscribe if you're new here. Now let's slowly ease into this. Part 1. The room that is never empty. Picture the room you are lying in right now. The lights are off or dimming. The air around you feels still. If you reached your hand up into the dark space above your bed and asked what was there, the honest answer your body would give you is nothing. Just air, and beneath the air, just emptiness. That is the intuition every human being is born with. Space is the stage. Matter is the actor. When you remove the actor, the stage remains, silent and bare, waiting. That intuition is wrong. It has been wrong for almost 100 years, and the way it is wrong turns out to be one of the strangest and most quietly terrifying discoveries in the history of physics. Let's start with what classical physics believed, because you have to understand the old, comfortable picture before you can appreciate how thoroughly it collapsed. In the world of Isaac Newton, space was a container. It had 3 dimensions, it stretched out infinitely in every direction, and it did nothing. It did not push, it did not pull, it did not hum with any hidden activity. It was the emptiest kind of empty you can imagine, a perfect mathematical backdrop against which real things, planets, apples, cannonballs, went about their business. If you removed every particle of matter from a region of space, if you took out every atom, every photon, every stray speck of dust, what remained was nothing. True, absolute, silent nothing. This picture survived largely intact even after Einstein rewrote the rules of space and time in the early 20th century. General relativity gave space a new kind of reality. It could stretch, it could curve, it could bend around massive objects like a stretched sheet of rubber. But even in Einstein's universe, if you took all the matter and energy out of a region, what was left behind was still, in principle, nothing. A geometrical stage, curved or flat depending on what was nearby, but empty of content. Then came quantum mechanics, and quantum mechanics does not like the word nothing. It never has. It cannot tolerate it, in fact, and the reason why takes us to one of the strangest ideas in all of science, a principle so counterintuitive that even the physicists who discovered it spent years trying to explain it away. The idea is called the uncertainty principle, and you have probably heard a simplified version of it. You cannot know both the position and the momentum of a particle with perfect precision at the same time. The more precisely you pin down where something is, the less precisely you can know how fast it is moving, and vice versa. This is usually taught as a statement about measurement, about the limits of what an observer can know. But that framing, while not wrong, hides something much deeper and much stranger. The uncertainty principle is not really about the limits of our instruments. It is a statement about what reality is willing to permit. Werner Heisenberg formulated this principle in 1927, working out the mathematics of the new quantum theory that he and Niels Bohr and Erwin Schrödinger and a handful of others were assembling almost feverishly across a handful of years in the 1920s. And one of the quieter, less publicized consequences of his uncertainty relation turned out to apply not just to position and momentum, but to energy and time. You cannot know the exact energy of a system at an exact moment in time. The more precisely you try to pin down a moment, the more the energy at that moment becomes genuinely, fundamentally uncertain. Not uncertain because you lack a good enough clock. Uncertain because the universe itself has not decided. Now sit with what that means for empty space. Take a region of space, remove every particle, remove every photon, cool it down as close to absolute zero as the laws of thermodynamics will allow. You now have, by every classical definition, nothing, zero energy, perfect emptiness. But the uncertainty principle will not let that zero sit still. If the energy of that region were exactly zero for exactly zero uncertainty forever, that would violate the energy-time uncertainty relation. The mathematics simply does not allow a region of space to hold a perfectly fixed value of exactly nothing across a perfectly fixed span of time. Something has to give. And what gives, according to quantum field theory, is that the energy of the vacuum is permitted to fluctuate. Briefly, locally, constantly, particles and their antiparticle partners are permitted to flicker into existence out of literally nothing, exist for an interval so brief it makes the word instant feel slow, and then annihilate each other and vanish back into the vacuum they came from. Physicists call these virtual particles, and the name is doing careful work. They are not virtual in the sense of being fake or imaginary. They are virtual in the sense that they cannot be directly observed the way a real, lasting particle can. They exist only as a brief accounting trick borrowed against the uncertainty principle's own rules and paid back before anyone can catch them at it. An electron and a positron might blink into being, exist together for a fraction of a second, and vanish. A photon might do the same. This is happening, according to quantum field theory, everywhere, all the time, in every cubic centimetre of what you have always called empty space, including the space between your fingers right now. This is the first big reframing you need to hold on to tonight, because everything else in this story builds on it. Empty space, in modern physics, is not a stage with nothing on it. It is a stage that is never actually cleared. The vacuum is not the absence of activity. It is a very particular, very low, but never quite zero state of activity. Physicists have a specific name for it. They call it the vacuum state, or sometimes the ground state, and the word ground is chosen deliberately. It means the lowest possible energy configuration a system can have. Not zero energy, the lowest energy. There is a difference, and that difference is the entire subject of tonight's story. Think of it this way. Imagine you are looking at a perfectly calm ocean at night. No wind, no boats, no visible waves. From a distance it looks like a flat, silent, motionless sheet of black glass. But get close enough, with sensitive enough instruments, and you find that the surface is never actually still. It trembles with microscopic ripples, thermal jostling at the molecular level, an endless quiet vibration that never fully stops because the temperature of the ocean is never actually absolute zero. The stillness was always an illusion of distance and inattention. Quantum field theory says the vacuum of space is exactly like that ocean, except colder than any ocean could ever be, and the ripples are not thermal, they are quantum, and they never, under any circumstances, go away. So here is the question that is going to carry us through the rest of tonight. If empty space is genuinely never empty, if it is filled edge to edge with these fleeting quantum fluctuations, these virtual particles winking in and out of existence faster than light itself could report on them, then that activity should have consequences. Energy is energy, however fleeting, however virtual, and in Einstein's universe, energy and mass are the same currency, exchangeable through the most famous equation ever written. If the vacuum has energy, the vacuum should have weight. It should push and pull. It should show up somewhere, in some measurement, in some observable effect on the world. And it does. That is not a hypothesis. That is the next part of tonight's story, because in 1948, a Dutch physicist sat down and worked out exactly what should happen if you took two ordinary, uncharged, unremarkable metal plates and held them apart in a perfect vacuum, close enough together that the emptiness between them started to matter. What he predicted, and what experimenters decades later actually measured, is one of the strangest and most quietly beautiful conformations in the entire history of physics. Nothing, it turns out, can push. Part 2. The Push of Nothing. His name was Hendrik Casimir, and in 1948 he was working at the Philips Research Laboratories in the Netherlands, a place better known at the time for light bulbs and radio tubes than for rewriting anyone's picture of the vacuum. Casimir was not chasing some grand philosophical question about the nature of nothing. He was doing something far more modest and far more interesting for exactly that reason. He was trying to explain a strange, slightly inconvenient discrepancy that colleagues at Philips had noticed in the behavior of colloidal particles, tiny suspended specks that seemed to attract each other slightly more strongly than the existing theory predicted at very short distances. Casimir went looking for the missing piece. What he found, when he worked through the mathematics of quantum electrodynamics applied to that problem, was not a small correction. It was an entirely new kind of force, hiding in plain sight, built directly out of the vacuum fluctuations we just spent the last part describing. Here is the thought experiment Casimir actually worked through, and it is worth sitting with slowly, because it is one of the strangest and most elegant pieces of reasoning in 20th century physics. Imagine two flat, uncharged metal plates. Not magnets, not batteries, nothing exotic, just ordinary electrically neutral metal. The kind of plate you could hold in your hand and feel nothing from at all. Now place them parallel to each other in a perfect vacuum and bring them close together, closer than the width of a human hair, close enough that the gap between them is measured in micrometers rather than millimeters. Classically, nothing should happen. There is no charge on the plates to attract or repel. There is no matter in the gap between them to push or pull on anything. By every rule of pre-quantum physics, those two plates should simply sit there, motionless relative to each other forever, feeling absolutely no force at all. But remember what we established a moment ago. The vacuum is not empty. It is filled with virtual particles flickering in and out of existence, and more specifically, it is filled with virtual photons, fluctuations of the electromagnetic field itself, popping into brief being at every possible wavelength, everywhere, all the time. Outside the two plates, in the open vacuum, virtual photons of every conceivable wavelength are permitted to exist. There is no restriction. The open vacuum can support fluctuations of any size, long ones, short ones, every wavelength in between. But inside the narrow gap between the two plates, something changes. A metal plate, being electrically conductive, imposes a boundary condition on the electromagnetic field. Certain wavelengths simply cannot fit between two conducting plates, the way a guitar string can only vibrate at specific wavelengths determined by its length. Only wavelengths that fit neatly, an integer number of times, into the gap between the plates are permitted to exist there. Every other wavelength, every fluctuation that does not fit the geometry, is forbidden inside the gap, even though it remains perfectly permitted outside. The consequence is subtle, but devastating in its implications. There are more possible vacuum fluctuations, more virtual photon wavelengths, existing in the open space outside the plates than there are permitted to exist in the cramped space between them. And more fluctuations means more energy density. The vacuum outside the plates has a higher energy density than the vacuum trapped between them, and energy density differences in a universe governed by quantum field theory translate directly into force. The result is that the two plates are gently, relentlessly pushed toward each other, not because they are attracting one another in any conventional sense, because there is more quantum vacuum pressure pushing in from the outside than there is pushing out from the inside. The plates are not pulling, they are being squeezed together by nothing, by the mismatch between one flavor of nothing and another flavor of nothing. Casimir published this prediction in 1948, and for the better part of 40 years it remained exactly that, a prediction, elegant on paper, mathematically clean, but agonizingly difficult to actually measure in a laboratory. The predicted force is astonishingly small. At a separation of about 1 micrometer, roughly 1/100th the width of a human hair, the Casimir force between two plates works out to something on the order of a 10,000th of an ounce per square inch of plate. To detect a force that's small, experimenters needed surfaces flat and parallel to a precision that simply did not exist with the technology of the 1950s or 1960s. Stray electrostatic charges, tiny surface irregularities, unwanted vibrations, any of these could swamp a signal that faint. It took until 1997 for a physicist named Steve Lamoureux, working at the University of Washington, to measure the Casimir force with real precision, confirming Casimir's 50-year-old prediction to within about 5%. Since then, the effect has been measured again and again with ever-increasing precision, using everything from torsion pendulums to micro-electromechanical systems, tiny engineered devices no larger than a grain of sand, specifically built to be sensitive enough to feel the push of the vacuum itself. Sit with that for a moment, because I do not want you to let it pass by too quickly. We have built machines on Earth, in ordinary laboratories, sensitive enough to directly measure the mechanical force exerted by empty space rearranging itself around two pieces of metal. This is not a thought experiment anymore. This is not a mathematical curiosity confined to chalkboards and journal articles. Nothing pushes. We have felt it push. We have written down the number. And it gets stranger the closer you look, because the Casimir effect is not some isolated party trick confined to metal plates in laboratories. It shows up in various forms throughout the architecture of the physical world in ways that are easy to miss precisely because they are so ordinary. The stability of certain configurations in nanotechnology depends on accounting for Casimir forces, because at scales of a few nanometers, The pressure from vacuum fluctuations becomes strong enough to make microscopic machine parts stick together. A phenomenon engineers call stiction, and it is a real practical headache in the design of microelectromechanical systems. Some biologists and biophysicists have even investigated whether Casimir-like forces play a subtle role in certain biological structures, though that research remains far more speculative and contested than the well-established physics of the plates. But here is the deeper point, the one that is going to carry us into the next part of tonight's story. The Casimir effect proves, beyond any reasonable scientific doubt, that the vacuum fluctuations predicted by quantum field theory are not merely a mathematical bookkeeping device. Some convenient fiction physicists use to make their equations behave. They are real. They have physical, measurable, repeatable consequences in the world. The 0-point energy of the vacuum, the residual energy that remains even after you have removed every particle, every photon, every last speck of ordinary matter from a region of space, is not a theorist's fantasy. It is a force you could, in principle, feel with your own fingertips if they were small enough and precise enough to notice a push measured in 10,000ths of an ounce. And once you accept that the vacuum has energy, once you accept that this energy is not merely theoretical but measurable, a very natural, very dangerous question follows immediately behind it. If the vacuum has energy, and energy according to Einstein is equivalent to mass, then the vacuum must have a kind of weight, a kind of gravitational presence. Empty space itself should gravitate ever so slightly the way any other form of energy in the universe gravitates. And if empty space gravitates, then it should be possible, at least in principle, to actually go out and measure how much it weighs by looking not at a laboratory tabletop, but at the largest possible laboratory available to any physicist, the universe itself. That is where we are going next, because in 1998, two teams of astronomers, using nothing more exotic than exploding stars billions of light years away, stumbled onto exactly this measurement. And what they found did not simply confirm that the vacuum has weight. It revealed that the vacuum's weight is actively, relentlessly reshaping the future of everything that exists. Part 3. The exploding stars that weighed nothing. In the middle of the 1990s, two rival teams of astronomers were racing each other toward the same measurement for what seemed at the time like a straightforward if difficult cosmological question. Not whether the vacuum has weight. Nobody was thinking about that yet, not directly. The question they were actually trying to answer was simpler and everyone assumed far less strange. How much is the expansion of the universe slowing down? This was, in the mid-1990s, considered one of the last great unresolved numbers in cosmology, but not a mysterious one. The logic was almost embarrassingly straightforward. The universe has been expanding since the Big Bang. Everyone agreed on that. The evidence for an expanding universe had been solid since Edwin Hubble's observations back in the 1920s. But gravity, everyone also agreed, is attractive. Every particle of matter in the universe pulls on every other particle of matter in the universe. And the combined pull of everything on everything else should be acting like a brake. The universe should be expanding, yes, but that expansion should be gradually, gently decelerating, the way a ball thrown up into the air decelerates as gravity pulls it back down. The only real question, in the minds of most cosmologists in 1995, was how much deceleration there was. Enough to eventually stop the expansion entirely and pull the universe back into a big crunch. Or just barely not enough, letting it coast outward forever, slowing but never quite stopping. To measure that deceleration, both teams, one called the Supernova Cosmology Project, led by Saul Perlmutter, and the other called the High Z Supernova Search Team, led by Brian Schmidt and including Adam Ries, turned to a very particular kind of exploding star called a Type 1 supernova. These explosions occur when a white dwarf star, the dense, burnt-out core of a star roughly the mass of our Sun, slowly siphons material off a companion star until it crosses a very precise, very consistent mass threshold and detonates. Because that threshold is nearly identical everywhere in the universe, these explosions reach nearly identical peak brightness wherever and whenever they occur. That makes them what astronomers call standard candles, an object bright enough to see across billions of light years and consistent enough that you can use its apparent brightness to calculate exactly how far away it is. The logic of the experiment was elegant. Find distant supernovae, measure how bright they appear. Compare that to how bright they should be if the universe had been expanding at a constant rate the whole time. If the expansion had been decelerating, distant supernovae, ones whose light left them billions of years ago when the universe was expanding faster, should actually appear slightly brighter than a simple constant expansion model would predict, because the space their light had to cross was, on average, smaller than expected. Both teams expected to measure exactly that, a small, modest deceleration, a number confirming what gravity, applied to a universe full of matter, had always demanded it should be. What they found instead, when the data finally came in during 1998, stunned both teams so completely that each one spent months independently checking and rechecking their own results, assuming they had made some catastrophic error before either was willing to publish. The distant supernovae were not brighter than expected. They were fainter. Consistently, systematically fainter across every distance they measured. And fainter meant farther away than a decelerating universe could explain. The only way to account for it was if the expansion of the universe had not been slowing down at all. It had been speeding up. This was, and remains, one of the single most surprising results in the history of observational science. Not because acceleration was theoretically forbidden, general relativity had always technically permitted the possibility, but because nobody expected it, nobody was looking for it, and it directly contradicted the working assumption that had guided cosmology for the better part of a century. Gravity pulls, it does not push. And yet here was the universe, unmistakably, undeniably, pushing itself apart faster and faster with each passing billion years. The discovery earned Perlmutter, Schmidt, and Ries the Nobel Prize in Physics in 2011, and it forced cosmologists to reach for a mechanism that could produce this kind of repulsive, accelerating effect on the largest scales imaginable. And there was, as it turned out, already a candidate sitting quietly in the mathematics of general relativity, waiting, largely unused, for exactly this moment. Back in 1917, just 2 years after publishing his general theory of relativity, Einstein had inserted an additional term into his own field equations, a constant value he called the cosmological constant, represented by the Greek letter lambda. His motivation at the time had nothing to do with acceleration or dark energy, concepts that did not exist yet even as ideas. Einstein added the term because his equations, left in their original form, insisted that the universe could not be static. It had to be either expanding or contracting, and in 1917 the prevailing assumption, shared by essentially every astronomer alive, was that the universe was fixed, eternal, unchanging, a single stable galaxy of stars that had always looked roughly the way it looked now. So Einstein tuned his cosmological constant to exactly cancel out the natural tendency of matter to collapse under its own gravity, producing a static, stable model of the cosmos. When Edwin Hubble's observations in the late 1920s revealed that the universe was, in fact, expanding, Einstein abandoned the cosmological constant entirely, reportedly describing it in later years, at least according to a second-hand account from the physicist George Gamow that historians have never been able to fully verify, as his greatest blunder. The term sat unused, an awkward historical footnote, for the better part of 70 years. Then in 1998, cosmologists needed exactly what Einstein's abandoned constant provided. A term in the equations of general relativity capable of producing a repulsive expansion-accelerating effect on the largest scales, one that did not dilute as the universe expanded, one that behaved mathematically like a fixed, unchanging property of empty space itself. And that is the precise moment where the story of the supernovae and the story of the vacuum fluctuations we spent the last 2 parts building suddenly, unexpectedly collide. Because if you ask what physical mechanism could actually produce a cosmological constant, what could actually fill empty space with a uniform, unchanging density of repulsive energy, quantum field theory already had an answer sitting right there. The zero-point energy of the vacuum. The same fluctuating sea of virtual particles that pushes 2 Casimir plates together in a laboratory should, in principle, also fill the entirety of empty space with a uniform background energy density. And crucially, unlike ordinary matter, which thins out and becomes less dense as the universe expands, the energy of the vacuum does not dilute. Every new cubic meter of space that comes into existence as the universe expands comes preloaded with exactly the same vacuum energy density as every other cubic meter. There is always more of it, because there is always more space. This is precisely the kind of substance you need to explain cosmic acceleration. As the universe expands, ordinary matter and radiation become increasingly diffuse, spread thinner and thinner across an ever-growing volume, and their gravitational pull on the expansion weakens correspondingly. But the vacuum energy stays exactly as dense as it always was, undiluted, unchanging. And its repulsive effect, rather than shrinking, comes to dominate more and more completely over cosmic time. Early in the universe's history, when matter was densely packed, gravity's attractive pull from all that matter overwhelmed the vacuum's gentle repulsion, and the expansion decelerated, just as everyone originally expected. But roughly 5 billion years ago, as matter thinned out across an ever larger volume, the balance tipped. The vacuum's repulsion began to win, and it has been winning more and more decisively ever since. Astronomers gave this mysterious repulsive component of the universe a name almost immediately: dark energy, and today. Based on decades of increasingly precise measurements combining supernova data, the cosmic microwave background, and the large-scale clustering of galaxies, we know its share of the total energy content of the universe with remarkable precision. Dark energy accounts for roughly 68% of everything that exists. Dark matter, a separate and equally mysterious substance we are not going to fully explore tonight, accounts for roughly 27%. And ordinary matter, every star, every planet, every atom in your body, every photograph ever taken through any telescope in the history of astronomy, makes up a mere 5% of the total energy budget of the cosmos. Sit with that ratio for a moment, quietly in the dark. The overwhelming majority of everything that exists is not made of stars or planets or people. It is, if the vacuum energy interpretation is correct, made of nothing, made of the empty space between things, doing exactly what quantum field theory said it should do all along, weighing something, pushing outward, gently and relentlessly reshaping the destiny of everything. It is, by any reasonable measure, a genuinely beautiful piece of scientific reasoning. Two separate, entirely independent lines of evidence, one from a laboratory on a tabletop measuring the push between two metal plates, the other from telescopes watching exploding stars billions of light years away, both pointing toward the same underlying idea. Empty space has energy. That energy has weight. That weight is shaping the universe. There was only one problem left, one last piece of homework before the story could be called complete. If dark energy really is the vacuum energy predicted by quantum field theory, then physicists should be able to calculate its value directly, using the same quantum mechanics that correctly predicts nearly everything else in the subatomic world to spectacular, staggering precision, and compare that calculation to the actual amount of dark energy astronomers had just measured in the sky. They did that calculation, and what came out the other end was not a small discrepancy, not an embarrassing rounding error requiring a modest correction. It was a number so catastrophically, so almost comically wrong, that it remains, to this day, the single worst quantitative prediction ever produced by any theory in the history of physics. That is where we are going next. Part 4. The worst prediction ever made. Let's do the calculation properly, slowly, the way a physicist actually approaches it, because the size of the failure only really lands once you understand exactly what is being added up. Quantum field theory treats every particle in the universe not as a tiny billiard ball moving through empty space, but as a ripple, a localized excitation in an underlying field that fills all of space. There is an electron field permeating everywhere, and what we call an electron is a particular kind of vibration in that field. There is a photon field. There is a field for every particle in the standard model, quarks, neutrinos, the Higgs, all of them, each one spread out uniformly across the entirety of space, whether or not any actual particle happens to be present at a given location. And here is the crucial part, the part that connects directly back to everything we established in part 1. Each one of these fields, even in a region with no particles present at all, still has a 0-point energy. Just like the electromagnetic field fluctuating between the Casimir plates, every quantum field in nature is forbidden by the uncertainty principle from sitting at a perfectly quiet, perfectly zero energy state. Each field has its own restless hum, its own flaw of unavoidable fluctuation, and every one of those flaws contributes some non-zero amount of energy density to what we call the vacuum. To calculate the total vacuum energy density, in principle, all you have to do is add up the 0-point contributions from every quantum field in nature. In practice, this calculation runs into an immediate and deeply uncomfortable technical problem. The 0-point energy contributed by a quantum field is not the same for every possible wavelength of fluctuation. Very long wavelength fluctuations contribute a small amount of energy. Very short wavelength fluctuations, correspondingly, contribute more. And quantum field theory, in its rawest, most naive form, permits fluctuations of arbitrarily short wavelength all the way down to 0, meaning that if you try to sum up the contributions from every possible wavelength, the total comes out formally infinite. Physicists have known about this problem, called the ultraviolet divergence, since nearly the earliest days of quantum field theory, and there is a broadly accepted way to handle it, at least well enough to get a finite, sensible answer. You do not trust the theory all the way down to zero wavelength. You trust it only up to the energy scale where you have good physical reason to believe new physics, physics we do not yet understand, must take over. The most natural, most conservative place to draw that line is called the Planck scale, an extraordinarily tiny length, about 1.6 times 10 to the negative 35th meters, below which our current understanding of gravity and quantum mechanics is expected to fundamentally break down. The same boundary we touched on when we talked about the singularity at the birth of the universe in an earlier episode of this series. Below the Planck scale, space and time themselves may not even have their ordinary meaning anymore. So physicists cut the calculation off there, summing up the 0-point contributions from every quantum field at every wavelength longer than the Planck length, and stop. Do that calculation using the standard model of particle physics and general relativity, and you get a predicted vacuum energy density, a real, specific, calculable number in units of energy per unit volume, the theoretical weight of empty space. Now compare that number to the actual amount of dark energy astronomers measured pouring out of the supernova observations, and later confirmed with extraordinary precision by satellite measurements of the cosmic microwave background, the same afterglow of the early universe we discussed at length in an earlier chapter of this series. The two numbers do not agree. They do not agree by a small amount. They do not agree by a large amount. They disagree by roughly a factor of 10 to the 120th power. 1 followed by 120 zeros. I want you to sit with that number for a moment, because it is genuinely, almost physically difficult for the human mind to process a discrepancy of that size, and every ordinary analogy we reach for immediately fails to do it justice. 10 to the 24th is already larger than the number of stars in the observable universe. 10 to the 80th is roughly the number of atoms in the observable universe. 10 to the 120th does not have a comfortable everyday comparison because nothing in ordinary experience, nothing in the entire observable cosmos is built on a scale anywhere close to it. If you tried to express the ratio using every particle in the observable universe as a single unit of counting, you would run out of particles to count with by a margin so enormous that adding more particles would not meaningfully help. Here is one way physicists sometimes try to convey the size of the failure, and even this analogy strains under the weight of the actual number. Imagine you were asked to predict the mass of a single grain of sand using your very best available physics, and your calculation came back suggesting that grain of sand should weigh more than every star, every planet, every galaxy in the entire observable universe combined. Not slightly more. Overwhelmingly, absurdly more. That is roughly the flavour, the emotional shape of what quantum field theory does when it tries to predict the energy density of empty space. It is not a near miss. It is a complete, catastrophic mismatch between two numbers that are supposed to describe exactly the same physical quantity. And the discomfort here goes deeper than simply having a big error bar. This is not a case of sloppy measurement or an unrefined technique waiting for a better experiment to sharpen it. Quantum field theory, applied to essentially every other problem physicists have ever thrown at it, is spectacularly, almost unnervingly accurate. The magnetic moment of the electron, a quantity that quantum electrodynamics predicts and that experimenters have independently measured, agrees between theory and observation to better than 1 part in a trillion, one of the most precisely verified numbers in the entire history of science. This is not a shaky, unreliable framework prone to wild errors. It is, by nearly every other measure available, the most successful physical theory human beings have ever constructed. And that is exactly what makes the vacuum energy catastrophe so disturbing rather than merely embarrassing. The theory is not failing because it is a bad theory. It is failing at exactly the one calculation where it should, by every reasonable expectation, be at its most confident, its most straightforward, its most directly connected to the deepest structure of reality. Asking quantum field theory to predict the energy of empty space is, in some sense, the single most fundamental question you can ask it. It is not a complicated many-body problem, not some messy interaction of countless particles under difficult experimental conditions. It is the simplest possible question. What is the energy of nothing at all? And on that question, on the most basic question imaginable, the theory produces an answer wrong by more than 100 orders of magnitude. Physicists have spent decades searching for some way to soften this description, some technical loophole that would shrink the discrepancy down to something merely large rather than something absurd. And there are legitimate technical arguments about exactly how the calculation should be framed, about which cut-off scale is truly the correct one to use, about whether summing naively over every quantum field the way we just described is even the physically correct procedure in the first place. Some more careful treatments bring the discrepancy down from 120 orders of magnitude to something more like 60, particularly if you use a lower energy cutoff tied to the scale of electroweak symmetry breaking rather than the full Planck scale. None of these refinements come remotely close to making the problem small. 60 orders of magnitude is still an incomprehensibly, unforgivably large mismatch. It is simply a slightly less unforgivable one. This is what physicists mean, without any exaggeration or rhetorical flourish, when they call this the worst prediction in the history of science. Not the least precise, not the most controversial, the worst in the specific and technical sense that no other confirmed prediction made by any accepted physical theory has ever missed its observed value by anywhere close to this magnitude, while the underlying theory remains, in every other application, one of the most trusted and rigorously verified frameworks we possess. So what is actually going on here? What is the universe trying to tell us, hiding somewhere inside 120 orders of magnitude of missing energy? There are, broadly, 3 ways physicists have tried to make sense of the gap, and none of them, I should tell you honestly and up front, is fully satisfying. None of them has become the accepted, settled answer. Each one opens its own strange door. The first possibility is that the naive calculation, the one that simply adds up 0-point contributions from every known quantum field up to the Planck scale, is simply the wrong calculation to be doing. Perhaps there is some deeper, currently unknown physics, some symmetry, some cancellation mechanism that we have not yet identified, which suppresses almost all of that predicted vacuum energy, leaving only the tiny residual that we actually observe pouring out of the supernova data. This is, in some sense, the most conservative and hopeful possibility, because it suggests the discrepancy is not evidence that something is deeply broken in our understanding of reality, but rather evidence that we are simply missing a piece of the puzzle, a piece that future physics might eventually supply. The second possibility is stranger, and it involves an idea called supersymmetry, a theoretical framework proposing that every known particle in the standard model has a partner particle, a superpartner, with different quantum properties, but related mass and interactions. One of the appealing features of supersymmetry, on paper, is that the zero-point energy contributions of these hypothetical superpartner particles come with the opposite mathematical sign to their ordinary counterparts, meaning that in a perfectly supersymmetric universe, the vacuum energy contributions from ordinary particles and their superpartners would cancel out almost exactly, leaving a net vacuum energy of precisely zero. This was, for a long time, considered one of the most elegant potential resolutions to the entire problem. There was just one difficulty. Decades of searching at particle accelerators, including the Large Hadron Collider at CERN, have failed to find any experimental evidence that supersymmetric particles actually exist at the energy scales physicists expected them to appear. If supersymmetry is real at all, it must be badly broken, meaning the superpartners, if they exist, are far heavier and far more elusive than originally hoped. And the elegant cancellation the theory promised no longer works cleanly enough to explain why the observed vacuum energy is so small. And the third possibility is the strangest of all, the one that makes even seasoned physicists visibly uncomfortable when they discuss it, because it does not try to explain the number at all. It tries to explain why we should not have expected to be able to explain it. That idea is called the anthropic principle, and it is where we are going to spend some real time in the next part of tonight's story, because it takes us somewhere far stranger than a single laboratory, or a single universe, or a single number written on a chalkboard. Part 5. The universe that had to be almost empty. Let's follow the strangest of the three explanations all the way down, because it does not begin with more physics. It begins by asking a completely different kind of question. Instead of asking why the vacuum energy has the specific tiny value we measure, it asks whether that question is even the right one to be asking in the first place. Here is the uncomfortable seed of the idea, and it comes from a very simple thought experiment. Imagine, for a moment, that the vacuum energy of our universe had come out with almost any other value than the one it actually has. Not a slightly different value. Any other value, drawn more or less at random from the astronomically vast range of possibilities that the raw, uncorrected quantum field theory calculation seems to permit. If the vacuum energy had come out even modestly larger and positive, if it were, say, merely a few hundred times larger than the tiny value we actually observe, rather than an incomprehensible 120 orders of magnitude larger, something catastrophic would have happened in the earliest moments of cosmic history. A vacuum energy that large would have driven the expansion of space so violently, so overwhelmingly, that matter would never have had the chance to clump together under gravity at all. Every particle of matter created in the aftermath of the Big Bang would have been flung apart from every other particle before gravity could pull any of it into the seeds of galaxies. No stars, no planets, no slow, patient accumulation of atoms into anything resembling structure. Just an ever-thinning mist of particles, forever separating, forever alone, in a universe expanding too violently to ever build anything at all. And if the vacuum energy had instead come out strongly negative rather than the extremely small positive value we measure, the outcome would have been just as fatal to complexity, though in the opposite direction. A sufficiently negative vacuum energy acts like an additional attractive force layered on top of ordinary gravity, and depending on its magnitude, it could have caused the universe to stop expanding entirely, reverse course, and collapse back in on itself in what cosmologists call a big crunch, all within a fraction of a second, long before atoms had time to form. Let alone stars, let alone galaxies, let alone anyone capable of building a telescope to ask what any of it meant. Between those two catastrophic extremes, one tearing everything apart before it can form, the other crushing everything back together before it can form, sits an extraordinarily narrow window of acceptable vacuum energy values, a window in which the repulsive push of empty space is gentle enough and delayed enough to allow gravity time to do its slow, patient work, pulling hydrogen and helium together into the first stars, letting those stars live and die and seed the cosmos with heavier elements, letting those elements coalesce into planets, letting chemistry unfold on those planets across billions of years, letting, eventually, something complex enough to wonder about all of this come into being. Our universe's vacuum energy sits inside that narrow window, astonishingly, precariously inside it. This is where a physicist named Steven Weinberg made a genuinely startling move back in 1987, more than a decade before the supernova teams had even directly measured that dark energy existed at all. Weinberg, one of the principal architects of the standard model of particle physics and no stranger to rigorous, hard-nosed calculation, approached the vacuum energy problem from an entirely different angle than anyone before him. Rather than trying to calculate the vacuum energy directly from first principles, and rather than trying to invent a new symmetry or cancellation mechanism to force it down to zero, Weinberg asked a more unusual question. Given that we exist, given that we are here, capable of measuring anything at all, what range of vacuum energy values would even be compatible with our own existence? Working through the physics of galaxy formation, Weinberg calculated that if the vacuum energy were much larger than a certain specific threshold, roughly comparable to the density of matter at the era when galaxies were first forming in the early universe, that expansion would become so overwhelming that galaxies, and by extension stars, and by extension anyone capable of doing physics, simply could not form at all. Using this reasoning, Weinberg predicted, years before anyone had directly measured it, that if a non-zero vacuum energy existed at all, its value should be small, remarkably small compared to what the naive theoretical calculation demanded, and roughly comparable in magnitude to the density of matter in the universe at the present cosmic epoch. When the supernova teams announced their discovery in 1998 and the actual measured value of dark energy came in, it landed almost precisely within the range Weinberg's anthropic reasoning had predicted more than a decade earlier. This is, by any reasonable standard, one of the more remarkable predictive successes in modern cosmology, and it came not from a deeper theory of what the vacuum energy fundamentally is, but from a calculation about what values of vacuum energy are even compatible with the existence of observers capable of measuring it. Now, this line of reasoning becomes genuinely powerful rather than merely a curious coincidence if it turns out that our universe is not the only one. And this is where the anthropic explanation for the vacuum energy problem connects to one of the strangest and most contested ideas at the frontier of modern theoretical physics, an idea sometimes called the multiverse, and more specifically in this context, the string theory landscape. Here is the reasoning, laid out carefully, because it deserves careful handling rather than breathless hype. String theory, one of the leading candidate frameworks for unifying quantum mechanics and gravity, though still unconfirmed by any direct experimental evidence, predicts an extraordinarily large number of mathematically consistent ways that the extra dimensions the theory requires could be folded up or compactified at scales far too small for us to directly perceive. Each distinct way of folding those extra dimensions corresponds, in the mathematics, to a different possible vacuum state, a different possible configuration of the fundamental fields of physics, each carrying its own value for things like particle masses, the strengths of the fundamental forces, and, Crucially for tonight's story, the value of the vacuum energy itself. Estimates for the number of distinct possible vacuum states within the string theory landscape run to something like 10 to the 500th power, a number so large that comparing it to the number of atoms in the observable universe, itself around 10 to the 80th, barely captures how enormous it actually is. Now bring back an idea we touched on gently in an earlier episode of this series. When we discussed the concept of eternal inflation, the theoretical picture in which the exponential expansion that smoothed and flattened the very early universe never fully stops everywhere, spawning pocket after pocket, bubble after bubble, each one becoming a separate region of space-time with potentially, in this picture, its own distinct vacuum state, drawn essentially at random from that vast landscape of 10 to the 500th possibilities. If this picture is correct, then what we call our universe, this bubble, this pocket, with its particular values for the mass of the electron, the strength of gravity, and the tiny, precisely tuned value of the vacuum energy, is just one region among an almost inconceivably vast ensemble of regions, each with its own vacuum energy drawn from that enormous landscape of possibilities. Most of those regions, the overwhelming majority of them, would have vacuum energy values catastrophically too large or too negative to ever allow galaxies, stars, or observers to form. They exist, if they exist at all, as sterile, empty, structureless expanses, forever unwitnessed, because there is no one inside them capable of witnessing anything. But a small fraction of that landscape, an incomprehensibly tiny slice of the total possibilities, would happen to land within the narrow, life-permitting window Weinberg identified. And it is only within that narrow slice, necessarily, unavoidably, that anyone would ever exist to look up into their own night sky and ask why the vacuum energy of their particular universe happens to be so surprisingly, so improbably small. Not because some deep law of physics forced that specific number, but because every other possible number would have produced a universe with nobody around to measure it. This is, without any exaggeration, one of the more philosophically uncomfortable ideas circulating in serious theoretical physics today, and it makes many physicists, including a good number of the ones who take it seriously as a mathematical possibility, visibly uneasy. It does not explain the vacuum energy in the way physicists usually mean explain, by deriving it from some deeper symmetry, some clean mechanism, some elegant equation that produces exactly the observed value and nothing else. It explains it by suggesting that the question itself, why is the vacuum energy this particular small number rather than some other number, might not have a deeper answer at all, beyond the fact that we could only ever find ourselves asking the question in a universe where the answer happened to permit our existence. And there is a real substantive scientific objection to leaning too heavily on this kind of reasoning, one that serious critics, including physicists who otherwise respect string theory and eternal inflation as legitimate mathematical frameworks, have raised forcefully. If a theory can, in principle, produce essentially any value of the vacuum energy somewhere across its landscape of possibilities, and if we are always going to find ourselves, by simple necessity, in one of the narrow slices where the value happens to be compatible with our own existence, then in what sense has the theory actually predicted anything at all? A framework flexible enough to accommodate any observed outcome risks becoming, in the memorable phrasing some critics have used, not even wrong, a structure so accommodating that it becomes difficult, perhaps impossible, to design any experiment that could ever falsify it. This tension between the genuine explanatory appeal of the anthropic argument and the deep discomfort many physicists feel about its testability remains unresolved. It sits, quietly and persistently, at the center of some of the most serious ongoing debates in theoretical physics today. Debates that stretch well beyond the vacuum energy problem alone and touch on the very nature of what counts as a scientific explanation. But whatever your own intuition tells you about the anthropic argument, whether it strikes you as a profound insight into the structure of reality or as an unsatisfying dodge dressed up in impressive mathematics, it does not change the observational facts we started with tonight. The vacuum has energy. That energy has weight. That weight is measurably, relentlessly reshaping the destiny of the universe, pushing galaxies apart from one another a little faster with every passing year, and the tiny, precisely balanced number describing exactly how strong that push is remains, regardless of which explanation you find most compelling, one of the deepest open puzzles in all of physics. There is one more thread of this story left to follow before we can begin to widen out toward a close, and it takes us back down to the smallest possible scales, back to the particle physics we touched on briefly a few minutes ago, because the vacuum energy catastrophe is not really one problem. It is at least two, tangled together, and untangling them changes how you should think about everything we have covered so far tonight. Part 6. Two mysteries wearing one number. There is a subtlety hiding inside everything we have covered so far tonight, one that is easy to miss on a first pass through this material, and it matters enough that it deserves its own quiet unpacking before we go any further. When physicists talk about the cosmological constant problem, they are actually describing two separate mysteries that have gotten fused together into a single number, and untangling them changes how you should feel about the whole story. The first mystery is the one we have already walked through carefully. Why is the vacuum energy density so absurdly catastrophically smaller than the naive quantum field theory calculation predicts? That is the 120 orders of magnitude problem. That is the worst prediction in the history of science. But there is a second, quieter mystery sitting right next to it, one that gets far less attention, but is, in some ways, even stranger. Even if you accept, for the sake of argument, that some unknown mechanism suppresses the vacuum energy down from its naive predicted value to something enormously smaller, why does it land precisely where it does? Not merely small. Small enough to be roughly comparable, right now, today, to the density of ordinary matter and dark matter in the universe. This is called the coincidence problem, and it deserves its name, because the timing involved is genuinely peculiar. As the universe expands, the density of matter dilutes steadily, growing thinner and thinner as the same fixed amount of stuff spreads out across an ever larger volume. The density of vacuum energy, by contrast, does not dilute at all. It stays exactly as dense as it always was, everywhere, forever, because there is always more space, and every new patch of space carries the same fixed vacuum energy with it. These two quantities, matter density and vacuum energy density, have been on wildly different trajectories across the entire history of the universe. Early on, matter density was overwhelmingly larger than vacuum energy density, by many, many orders of magnitude, because the early universe was so densely packed. Far in the future, vacuum energy density will overwhelmingly dominate, because matter will have thinned out across a volume that never stops growing. There is only one relatively brief window in the entire 14 billion year history of the cosmos, during which these two wildly different quantities happen to be roughly comparable in size, close enough to each other that the balance between them actually determines the current rate of cosmic acceleration in an interesting way rather than a trivial one. And we happen to be living inside that narrow window right now tonight as you listen to this. Not billions of years ago when matter completely dominated. Not billions of years from now when vacuum energy will completely dominate. Right now, in the brief, cosmically peculiar era when the two are close enough to compete. Is that a coincidence? Is it a clue pointing towards some deeper connection between matter and vacuum energy that we have not yet discovered? Some mechanism that ties the two together in a way current physics does not capture? Or is it, once again, a selection effect, the anthropic reasoning we just walked through, suggesting that this window of rough balance also happens to correspond, roughly, to the era when stars, planets, and observers capable of asking the question would exist? Because that timing is not entirely arbitrary either. Nobody knows. It remains, alongside the magnitude problem itself, one of the genuinely open threads in this story. Now let's fold in one more layer, because it changes the emotional shape of everything we have covered so far tonight. And it is worth sitting with before we start winding this episode down. Some of the discrepancy in the original calculation, it turns out, is not really a mystery about nature at all. It is a mystery about the limits of our own theoretical tools. Remember that the naive calculation of vacuum energy involves summing contributions from every quantum field at every possible wavelength, all the way down to the Planck scale, the point at which our current understanding of physics is expected to break down entirely. That choice of cutoff is doing an enormous amount of quiet work in the calculation, and it is, frankly, something of an admission of ignorance dressed up as a technical assumption. We do not actually know what happens to space and time at scales smaller than the Planck length. We do not have a working theory of quantum gravity that tells us, with confidence, whether the smooth, continuous picture of space-time that general relativity and quantum field theory both quietly assume even remains valid down there. It is entirely possible, and a number of serious theoretical physicists consider it likely, that the true resolution to the vacuum energy problem is hiding inside physics we simply have not developed yet. Physics that only becomes relevant at scales we cannot currently probe with any existing or foreseeable experiment. This is, in its own way, a strangely comforting thought, and I want to leave you with it gently before we widen the lens one final time. The vacuum energy catastrophe is not necessarily evidence that quantum field theory is broken, or that general relativity is broken, or that either theory has failed us in some fundamental way. It may simply be evidence that we are trying to ask a question. What is the energy of empty space at the very smallest conceivable scales, using tools that were never designed to answer it, because the tools themselves stop being trustworthy exactly at the scale where the answer lives? That is not a failure of physics in the way it sometimes gets described in more sensational retellings of this story. It is physics doing something rare and valuable, quietly and honestly revealing, through the size of its own error, exactly where the edge of current human understanding actually sits. The equations are not lying to us. They are pointing, as precisely as anything in science ever has, directly at the gap in the map. And that brings us, gently, to the place where tonight's story has been leading all along. Part 7. What the vacuum is actually made of. Let's step back now, all the way back, and ask the question this whole night has been circling. Not why the numbers disagree, not which explanation is most fashionable among theorists this decade, just the plain question sitting underneath everything else. What is the vacuum actually made of? The honest answer, the one that emerges once you set aside all the competing explanations for the catastrophe and just look at what has been directly measured, is that the vacuum is made of possibility. Not possibility in some vague poetic sense. Possibility in a very precise mathematical sense. The specific kind of possibility that quantum field theory describes when it says that every field in nature, at every point in space, carries a non-zero probability of briefly departing from its lowest energy configuration. Think back to the Casimir plates for a moment, because that experiment is really the cleanest window we have into what this means physically. The plates did not measure the vacuum's mass directly, the way you might weigh an object on a scale. They measured the vacuum's willingness to rearrange itself under a constraint, its refusal to sit at a single boring fixed configuration even when there is nothing at all present to disturb it. Squeeze the space between two conductors and the vacuum responds, not with silence, but with pressure. Because you have restricted which fluctuations are allowed to exist inside the gap, and the vacuum outside the gap, unrestricted, unconstrained, pushes back. That is the deepest available answer to tonight's question, at least the deepest one current physics can offer. The vacuum is not a container waiting to be filled. It is not a stage waiting for actors. It is an active, restless field of possibility, one that is never permitted by the uncertainty principle to settle into true and total stillness, and that restlessness is not a metaphor. It has a measurable pressure, it has a measurable pull on the light of exploding stars 4 billion light years away. It has, whatever the correct final number eventually turns out to be, a weight. And here is the strange, quiet gift buried inside the catastrophe we spent most of tonight walking through. The fact that our calculation is wrong by 120 orders of magnitude is not, in the end, a story about failure. It is a story about how close we have actually come to touching something genuinely fundamental. You do not get a wrong answer that specific, that precisely calculable, unless you are asking a question that sits extremely close to the true architecture of reality. A theory that was simply confused about the nature of empty space would not produce a number at all. It would produce nonsense, or nothing, or an answer with no clear physical meaning whatsoever. Quantum field theory produces a number, a real, specific, calculable number. It is simply the wrong number by an almost unfathomable margin, and that specific kind of wrongness with structure, wrongness you can write down and compare against observation, is exactly the kind of failure that has, throughout the history of physics, tended to precede the deepest revolutions. This has happened before, more than once, and it is worth remembering as we start to close tonight's story. At the end of the 19th century, the theory describing how hot objects radiate light predicted, with perfect mathematical confidence, that any object at any temperature above absolute zero should radiate an infinite amount of energy at very short wavelengths, a prediction so absurd that physicists at the time nicknamed it the ultraviolet catastrophe. It was resolved not by patching the old theory, but by abandoning one of its core assumptions entirely. The assumption that energy could be exchanged continuously rather than in discrete packets, and that abandonment gave birth to quantum mechanics itself. The vacuum energy catastrophe carries an eerie structural resemblance to that earlier crisis. Another calculation that goes badly, spectacularly wrong, precisely at the smallest scales. Precisely where our current theories are pushed furthest beyond the regime they were built and tested for. Nobody can promise you that the resolution to tonight's mystery will be anywhere near as clean or anywhere near as world-changing as the birth of quantum mechanics was. It may turn out to require an actual, complete theory of quantum gravity, a framework we do not yet possess. One that finally explains what happens to space and time at the Planck scale, and in doing so, finally tells us how to correctly sum up the restless energy of every quantum field without running headlong into absurdity. It may turn out to require some version of the anthropic reasoning we discussed a few parts ago, an acceptance that certain features of our particular universe are not derivable from first principles at all, but are instead a consequence of which possible universes happen to be compatible with the existence of anyone capable of asking the question. It may turn out to require an idea nobody has thought of yet, sitting quietly in some future physicist's notebook, waiting what we can say with real confidence tonight is this: empty space is not empty. That is not speculation. That is measured, repeated, confirmed physics, sitting in laboratories on this planet right now, in devices small enough to hold in your palm, sensitive enough to feel the push of fluctuations that exist for less than a trillionth of a second before vanishing back into whatever it is they came from. And that same restless, weighing, pushing nothingness stretches out, uniformly, invisibly across every cubic meter of the observable universe, gently and relentlessly accelerating the separation of every galaxy from every other galaxy, a slow, patient, cosmic scale echo of the very same quantum uncertainty that governs the tiniest particle in your own body. You have spent this entire night lying in what feels like still, quiet darkness. But the space around you, the space between your fingers, the space filling this room has never once been still. It never has been, not for a single instant since the earliest fraction of a second after the universe began, and by every indication current physics can offer, it never will be. Somewhere in the trillions of quantum fields quietly fluctuating around you tonight, in the tiny, precisely balanced number that determines exactly how hard the vacuum pushes back against everything else that exists, there is an answer waiting. We do not have it yet. We have only the size of our own error, written out in 120 zeros, pointing, as clearly as anything in science ever has, toward the exact place where the map runs out. Part 8. The many attempts to tame the number. By now you have heard the shape of the problem from several angles, the laboratory push of the Casimir plates, the runaway acceleration written into the light of dying stars, and the catastrophic mismatch between what quantum theory predicts and what the sky actually shows. It would be natural to assume that physicists, faced with 120 orders of magnitude of embarrassment, simply shrugged and moved on to other problems. They did not. For the better part of 4 decades, some of the most capable theoretical minds alive have thrown themselves at this number, and it is worth walking through a handful of the more serious attempts. Not because any of them has solved it, but because the shape of their failures tells you almost as much as a success would have. The most conservative approach, historically, was simply to hope for cancellation. Quantum field theory, remember, sums up contributions from every field in nature, and in principle those contributions do not all have to carry the same sign. A field describing a fermion, a particle like the electron that obeys the Pauli exclusion principle, contributes a negative 0-point energy to the total vacuum sum. A field describing a boson, a particle like the photon that does not obey that exclusion, contributes a positive 0-point energy. If, by some deep organizing principle of nature, the universe contained exactly the right balance of fermionic and bosonic fields, their contributions could cancel almost perfectly, leaving only a tiny residual behind. the residual we actually observe. This is, at its heart, the appeal behind supersymmetry, the idea we touched on earlier, the theory proposing that every known particle has an undiscovered partner particle with the opposite statistical character. In a perfectly supersymmetric universe, every fermions's negative contribution would be exactly matched by its bosonic superpartner's positive contribution, and the total vacuum energy would come out to precisely zero, no catastrophe required at all. For a long stretch of the 1980s and 1990s, this was widely considered the most promising path forward, elegant, mathematically motivated, by considerations having nothing to do with the vacuum energy problem in the first place, and testable, at least in principle, at a high enough energy particle collider. The trouble is that supersymmetry, if it is a true feature of nature at all, is clearly not exact. We do not observe a supersymmetric partner for the electron with the electron's exact mass, floating around at everyday energies, and we would have noticed one by now if it existed. Any real version of supersymmetry has to be broken, meaning the superpartners, if they exist, are considerably heavier than their ordinary counterparts, hidden from us because producing them requires more energy than our accelerators can currently reach. And once supersymmetry is broken, the elegant, perfect cancellation it promised breaks along with it. You are left with a residual vacuum energy that depends sensitively on exactly how and at what scale the symmetry is broken. And getting that residual down to anywhere near the tiny value dark energy actually has requires a level of fine-tuning almost as uncomfortable as the original problem it was meant to solve. Decades of searching at the Large Hadron Collider have, so far, found no direct evidence of supersymmetric particles at all at any of the energy scales theorists once considered most promising, which has left this once favoured explanation looking considerably less certain than it did 20 years ago. A second family of attempts approaches the problem from an entirely different direction, by questioning whether dark energy is really a fixed, unchanging cosmological constant at all, rather than something dynamic, something that might be capable of evolving over cosmic time. These models generally go by the name quintessence, borrowing the old term for a mysterious fifth element once imagined to fill the heavens beyond earth, air, water, and fire. In quintessence models, the accelerating expansion of the universe is not driven by a fixed, immovable property of empty space itself, but by a genuine physical field. Similar in spirit to the inflaton field, believed to have driven the universe's exponential expansion in its first fraction of a second, except this field is imagined to be rolling slowly, gently, across an almost flat energy landscape today, in the current era of cosmic history, rather than in the earliest instant after the Big Bang. If dark energy really is a slowly evolving quintessence field, rather than a truly fixed constant, its strength could in principle have been different in the distant past, and could continue to change gradually as the universe continues to age. This is not idle speculation. It is directly testable, and it is being tested right now by one of the most ambitious astronomical surveys ever undertaken, the Dark Energy Spectroscopic Instrument, known as DESI, which has spent recent years mapping the three-dimensional positions of tens of millions of galaxies and quasars across an enormous volume of the observable universe, tracing the imprint of ancient sound waves frozen into the distribution of matter shortly after the Big Bang to measure, with unprecedented precision, exactly how the expansion rate of the universe has changed across billions of years of cosmic history. The early results, released in 2024, produced a genuine ripple of excitement and caution through the cosmology community, because when the DESI data was combined with older measurements of the cosmic microwave background and distant supernovae, the best fit to the combined data set favoured. Mildly but noticeably, a dark energy that is not perfectly constant after all, one whose strength may have been somewhat greater in the distant past and has been gently weakening ever since. The statistical significance of this hint, as of the most recent analyses, sits somewhere in the range of 2 to 4 standard deviations, tantalizing, genuinely interesting, but well short of the 5 standard deviation threshold physicists require before declaring something a confirmed discovery rather than an intriguing pattern that further data may yet wash away. It is worth pausing on what it would actually mean if that hint holds up under further scrutiny in the coming years. A genuinely evolving dark energy would be, in some ways, a harder problem than a simple, unchanging cosmological constant, not an easier one. A fixed constant, whatever else you might say about its bizarre calculated value, is at least conceptually simple. It requires no explanation for why it changes, because it does not change. An evolving dark energy demands an answer to a much sharper question. What is the physical substance that is doing the evolving? What determines the shape of the energy landscape it is rolling across? And why does that landscape happen to be so extraordinarily delicately flat that the field rolls across it as slowly as it apparently does? Trading a constant for a field does not remove the fine-tuning problem. It relocates it, dressing the same underlying mystery in new mathematical clothing. A third and considerably more radical family of attempts abandons the idea of new fields or new particles altogether, and instead asks whether general relativity itself, Einstein's description of gravity, might simply be incomplete at the largest cosmological scales, in something like the way Newtonian gravity turned out to be incomplete once physicists began probing the extremes of very strong gravitational fields and very high speeds. These modified gravity theories attempt to reproduce the observed acceleration of the universe without invoking any vacuum energy or dark energy field at all, by altering the geometric side of Einstein's equations rather than the energy side. Some of these models have shown genuine promise in narrow tests, and none of them has yet managed to reproduce the full sweep of observational successes that standard general relativity paired with a cosmological constant currently enjoys, from the precise structure of the cosmic microwave background to the detailed behavior of gravitational lensing across enormous cosmic distances. What all three of these approaches share, whatever their individual merits and shortcomings, is that none of them has yet produced the thing physics actually wants. A calculation from first principles that predicts the observed value of dark energy correctly, the way quantum electrodynamics correctly predicts the magnetic moment of the electron to 12 decimal places. Every path forward currently on the table requires accepting some new assumption, some new particle, some new field, some new departure from Einstein's original equations, whose existence has not yet been independently confirmed by any experiment. The gap between prediction and observation, the 120 orders of magnitude we spent so much of tonight sitting inside, remains. Honestly and without exaggeration, unresolved. Part 9. Listening for the vacuum's own voice. There is a quieter, more patient side to this story that rarely makes it into the more sensational retellings, and it deserves its own space here because it is where the actual ongoing work is happening, rather than waiting for a single decisive theoretical breakthrough to resolve the vacuum energy catastrophe from the armchair. A great deal of modern physics has instead turned toward listening, building better instruments, watching the sky more carefully, squeezing tighter and tighter constraints on the vacuum's behavior, hoping that nature, rather than mathematics alone, will eventually hand us the clue that theory has not yet managed to produce. The DESI survey we discussed a moment ago is only one piece of a much larger coordinated effort. The Euclid Space Telescope, launched by the European Space Agency in 2023, is currently in the process of mapping the shapes and distances of billions of galaxies across more than a third of the visible sky, tracing the way the gravitational pull of matter subtly distorts the light of more distant galaxies passing near it, a technique called weak gravitational lensing, in order to reconstruct, in exquisite detail, exactly how the large-scale structure of the universe, and by extension, the balance between matter and dark energy, has evolved across cosmic history. The Vera Rubin Observatory in Chile, which began its main science survey in 2025, is conducting an unprecedented 10-year photographic census of the entire visible southern sky, repeatedly, night after night, cataloguing tens of billions of galaxies and tens of thousands of supernovae, building a dataset so vast and so precise that even subtle deviations from a perfectly constant dark energy should, if they exist, eventually become impossible to hide. These are not experiments designed to answer a single narrow question. They are designed to do something more valuable and more patient than that. They are designed to keep tightening the vise around the possible answers, ruling out entire families of theoretical explanations one by one, narrowing the space of what dark energy could plausibly be. The same way particle physicists spent decades tightening the vise around where a supersymmetric particle could possibly be hiding, until the absence of a detection became, itself, a meaningful piece of information about the structure of reality. There is also a very different kind of experiment underway, one that circles back to exactly where tonight's story began, the Casimir effect itself. In the decades since Steve Lamoreaux's original 1997 confirmation, experimentalists have pushed Casimir force measurements to remarkable levels of precision, using microelectromechanical devices small enough to sit on the tip of a fingernail, engineered specifically to be sensitive to the faint, restless push of vacuum fluctuations at ever smaller separations between surfaces. Some researchers have gone further still, investigating what is sometimes called the dynamical Casimir effect, an extension of the original idea in which, rather than holding two plates perfectly still, you move one of them, or rapidly modulate the properties of the space between them, fast enough that the vacuum genuinely cannot keep up, and real, detectable photons, no longer merely virtual, are pulled directly out of empty space and left behind as the boundary conditions shift. This effect was first experimentally confirmed in 2011, using a superconducting circuit designed to mimic a mirror moving at a meaningful fraction of the speed of light, and it stands today as perhaps the single most direct, unambiguous demonstration available that the vacuum is not a passive backdrop, but an active medium capable of genuinely, measurably giving something up when you disturb it correctly. None of these laboratory experiments, it is important to say clearly, have yet closed the gap between the theoretical prediction and the cosmological measurement. The Casimir effect confirms that vacuum fluctuations are real and physically consequential. It does not, by itself, tell you why the total gravitating vacuum energy filling the universe comes out so many orders of magnitude smaller than the naive sum over every quantum field would suggest. These are related questions, but they are not the same question, and one of the quieter, more humbling lessons of the last several decades of research is just how difficult it has proven to build a bridge between the small-scale, laboratory-confirmed reality of vacuum fluctuations and the large-scale, cosmologically observed reality of dark energy. The two phenomena are almost certainly connected, Both are manifestations of the same underlying idea that empty space is not truly empty, but connecting them quantitatively with an actual working calculation that produces the correct number remains, as it has for decades, out of reach. There is a particular kind of intellectual humility that this story demands, and it is worth sitting with directly rather than glossing over. Physics, as a discipline, is generally very good at eventually closing gaps like this one. The history of the field is, in large part, a history of exactly this pattern, a stubborn discrepancy between theory and observation, resisting explanation for years or decades, until some reframing, some previously unconsidered idea, some new piece of mathematics or new class of observation finally dissolves it, usually in a way that, in hindsight, makes the earlier confusion look almost obvious. The precession of Mercury's orbit sat as an unexplained anomaly in Newtonian gravity for the better part of 60 years before general relativity accounted for it precisely, with no adjustable parameters required at all. The calculations simply falling out of the new theory naturally. The ultraviolet catastrophe and blackbody radiation sat unresolved for barely a few years before Max Planck's quantum hypothesis dissolved it entirely, launching an entirely new branch of physics in the process. The vacuum energy catastrophe has now been sitting, largely unresolved in its most essential form, for the better part of 4 decades since physicists first began to appreciate its full severity, and for more than 25 years since the direct cosmological measurement of dark energy turned it from a theoretical curiosity into an observationally confirmed crisis. That is a long time by the standards of physics for a problem this fundamental to remain open. It does not mean the problem is unsolvable. It may simply mean that the correct resolution requires ingredients, a working theory of quantum gravity, a genuine detection of new physics beyond the standard model, some conceptual reframing nobody has yet proposed, that have simply not arrived yet. The same way a working theory of general relativity had not yet arrived for the physicists puzzling over Mercury's orbit in the 1850s. What can be said with real confidence, standing where we are tonight, at the current edge of human understanding, is this: the vacuum has energy. That energy has weight. That weight is not a rounding error buried somewhere in the margins of an obscure calculation. It is, by current measurement, the single largest component of the entire energy content of the universe, larger than every star, every planet, every galaxy, every strand of the cosmic web combined. And the honest, careful attempt to calculate that weight from first principles, using the very same quantum field theory that correctly predicts nearly everything else we have ever measured about the subatomic world, fails so completely, so catastrophically, that the size of the failure has become itself one of the most important clues physics currently possesses about where its own understanding runs out. That is not a comfortable place to end an evening's thinking. But it is, in a very real sense, an honest one, and there is something quietly beautiful about sitting with a genuine, unresolved mystery rather than a manufactured one, a mystery that real telescopes and real laboratories, right now, tonight, are actively working to narrow, one careful measurement at a time. Part 10. What almost nothing weighs and why it matters for everything. Let's turn now gently toward consequence, because a mystery this large is not only an intellectual curiosity, it shapes the actual physical fate of everything that will ever exist, including you, including every person who has ever lived, including every star that has ever burned, and every planet that has ever formed around one. The weight of empty space is not an abstraction confined to chalkboards and telescope data. It is quietly, patiently writing the final chapter of the story of the cosmos. And it is worth understanding plainly and without exaggeration what that ending actually looks like. If dark energy is exactly what our current best model, the cosmological constant, describes, a truly fixed, unchanging property of space itself that never weakens and never strengthens, then the future of the universe is already, in broad outline, determined. The accelerating expansion we discovered through those exploding stars will simply continue, gently, relentlessly, forever. Galaxies that are not gravitationally bound to our own local group will, over the coming tens of billions of years, recede from us faster and faster, their light stretching to longer and longer wavelengths, until eventually, one by one, they slip beyond a boundary called the cosmic event horizon, a horizon we discussed at length in an earlier chapter of this series, and simply vanish from view, not through any dramatic event, but through the quiet, patient work of ever-accelerating separation. Run that process forward far enough, something on the order of 100 billion years from now, roughly 7 times the current age of the universe, and the night sky itself will have changed almost beyond recognition. The only galaxies still visible will be the handful gravitationally bound tightly enough to our own to have resisted the pull of accelerating expansion, our own Milky Way, merged by then with Andromeda into a single larger galaxy, along with a scattering of smaller companions. Every other galaxy, every one of the roughly 2 trillion currently visible from Earth, will have redshifted into permanent invisibility, their light stretched so far beyond any wavelength any conceivable instrument could ever detect that they will, for all practical purposes, cease to exist as observable objects at all, even though they will, of course, still be out there, simply beyond the reach of anyone left behind to look for them. This is in itself a genuinely strange thing to sit with quietly in the dark. Any civilization, anywhere in the universe, that happens to arise late enough in cosmic history, tens of billions of years from now, will inherit a sky containing only their own local cluster of galaxies, with absolutely no observational evidence remaining that a much larger, richer universe filled with billions of other galaxies ever existed at all. They would have no way from their vantage point of ever discovering the cosmic microwave background, no way of measuring the expansion of the universe the way we have, no way of ever deducing the Big Bang, because the very evidence that allowed us to piece this story together will have expanded permanently beyond anyone's reach by then. We happen to exist, and this is worth sitting with, at what may be an unusually fortunate moment in cosmic history, early enough that the evidence of our universe's origin and structure is still legible in our sky. Later observers will inherit a quieter, emptier, more mysterious universe than the one we are lucky enough to be looking out at tonight. There is, however, a considerably stranger and more violent possible ending, one that depends entirely on that unresolved question we discussed a few parts ago, whether dark energy is truly a fixed, unchanging constant, or whether it might instead be evolving over cosmic time. If future observations from DESI, from Euclid, from the Vera Rubin Observatory, from instruments not yet built, eventually confirm that dark energy has been strengthening rather than weakening, a scenario cosmologists call phantom dark energy, then the story does not end with a slow, gentle fade into isolated darkness. It ends in something considerably more dramatic. In a phantom dark energy scenario, the acceleration of cosmic expansion does not merely continue, it intensifies, growing stronger and stronger as time passes, rather than remaining constant or gradually weakening. Eventually, given enough time, that intensifying acceleration would grow strong enough to overcome not just the gravitational binding holding galaxies together, but the gravitational binding holding individual star systems together. Then the electromagnetic forces holding planets and stars themselves together. Then the forces holding molecules together. Then the forces holding individual atoms together. And finally, in the last conceivable fraction of a second, the nuclear forces holding the protons and neutrons inside atomic nuclei together. Everything at every scale would be torn apart, not through heat, not through collision, not through any conventional catastrophe at all, but through the literal geometric expansion of the space between every pair of particles in existence, growing faster than any force could ever hope to hold them together. Physicists have given this hypothetical ending a suitably blunt name. They call it the Big Rip. I want to be very careful and very honest with you here, because it would be easy, in a video like this one, to lean into that image for its drama and let it sit unchallenged. Current observational data does not require a phantom dark energy scenario. The best available measurements remain broadly, though not perfectly, consistent with a simple, fixed cosmological constant, the gentler ending described a few minutes ago, galaxies slowly fading beyond an ever-tightening horizon rather than everything being torn apart in a final cataclysmic instant. The recent hints from Deci, the ones suggesting dark energy might be weakening slightly over cosmic time rather than strengthening, if they hold up under further scrutiny, would actually point toward an ending gentler still than either of the scenarios just described, one in which cosmic acceleration eventually slows rather than intensifies. The honest, current state of the science is genuinely uncertain about which of these futures, if any of them precisely, awaits us, and that uncertainty is not a failure of the data. It is an accurate, honest reflection of how much we still do not know about the exact nature of dark energy. But notice something quietly remarkable buried inside all three of these possible endings: the gentle fade, the eventual slowing, and the violent tear. Every single one of them is determined entirely by the exact numerical value of that same tiny, precisely balanced number we spent so much of tonight sitting with, the weight of empty space, the number our best theoretical calculation gets wrong by 120 orders of magnitude, the ultimate fate of everything that exists, every star that will ever form, every planet that will ever cool into something capable of hosting life, every civilization that will ever look up into its own night sky and wonder what it is looking at, all of it hinges on a single, tiny, stubbornly unexplained number describing how much nothing weighs. That is, when you sit with it slowly, an extraordinary thing for a single unsolved problem in theoretical physics to be responsible for. Not merely an embarrassing gap in a calculation tucked away in some specialist journal, but the deciding factor in how the entire story of the universe eventually, inevitably, comes to a close. The vacuum is not a footnote to cosmology. It is, in a very real and very literal sense, cosmology's final chapter, still unwritten, waiting on a number we have not yet learned how to correctly derive. Part 11. Standing inside the mystery. There is a particular kind of vertigo that settles in once you have followed this story all the way to where we are now, and I want to name it honestly before we start to widen out toward a close, because I think it is worth feeling rather than rushing past. You began this evening lying in a room you assumed was simply empty around you. You now understand that the space filling that room is seething, quietly and continuously, with fluctuations that never stop, that those fluctuations have been directly measured pushing metal plates together in laboratories, that the same restless quantum activity fills every cubic meter of the observable universe, that it is actively, measurably accelerating the separation of every galaxy from every other galaxy, and that our best mathematical attempt to predict exactly how strong that push should be misses the true answer by more zeros than most of us will ever encounter in any other context in our entire lives. It would be easy, sitting with all of that, to feel a kind of unease about it. The sense that physics has somehow failed here, that 120 orders of magnitude of error represents some kind of crisis for the discipline as a whole. I want to gently push back against that reading, because I think it misunderstands what is actually happening, and I think the more accurate way to feel about it is closer to something like privilege than alarm. Consider what would have to be true for this problem to not exist at all. It would mean that quantum field theory, our best description of the very small, and general relativity, our best description of the very large, simply did not overlap anywhere, that there was no shared territory where the predictions of one could be meaningfully compared against the measurements enabled by the other. That would actually be the worse outcome, scientifically speaking, not the better one. It would mean we had two separate, disconnected theories, each successful within its own narrow domain, with no way of ever testing whether they were secretly describing the same underlying reality or two entirely incompatible ones. The vacuum energy catastrophe exists precisely because quantum field theory and general relativity do overlap, precisely because both theories are ambitious enough and successful enough within their own domains to make a genuine, falsifiable prediction about the exact same physical quantity, the energy density of empty space. The catastrophe is not a sign that physics has failed to connect these two theories. It is the direct, measurable consequence of physics having connected them just enough to discover that something is still deeply, interestingly wrong with how we understand the connection. That is worth sitting with slowly, because it reframes the entire emotional shape of tonight's story. 120 orders of magnitude is not a monument to human failure. It is a monument to how far we have already come, an almost unbelievably precise measurement of exactly how much further there is left to go. And there is a particular kind of quiet, generational privilege in being alive at exactly this moment in the history of this question. The physicists who first began to appreciate the full severity of this problem, working through the calculations in the late 1960s and 1970s, did not yet have a confirmed measurement of dark energy to compare their predictions against. They were staring at an absurd theoretical number with no direct astronomical confirmation that anything like an accelerating universe even existed at all. The 1998 supernova discoveries changed that permanently, turning a theoretical curiosity into a confirmed observational crisis almost overnight, and every year since has brought sharper instruments, larger surveys, tighter constraints, genuine hints like the recent DESI results of whether dark energy might be evolving rather than fixed. We are not waiting passively for someone else to solve this. We are, collectively, right now, in the middle of actively gathering exactly the kind of data that will eventually decide between the competing explanations we walked through tonight, the supersymmetric cancellation, the anthropic landscape, the evolving quintessence field, the possibility that the true answer requires physics nobody has yet imagined. There is a version of this story, easy enough to tell, that treats the vacuum energy catastrophe as evidence that physics has reached some kind of limit, that the deepest questions about reality are simply beyond what human minds and human instruments will ever be able to resolve. I do not think that is the correct lesson to take from tonight, and I do not think it is the lesson the history of this particular problem actually supports. Every major crisis like this one that physics has faced before, the ultraviolet catastrophe, the perihelion of Mercury, the missing mass in galaxy rotation curves that first pointed toward dark matter, has eventually yielded. Not always quickly, not always in the way anyone initially expected, but it has yielded, revealing along the way something genuinely new about the structure of reality that nobody could have simply guessed their way toward without first being forced, uncomfortably, up against the wall of an unresolved contradiction. The vacuum energy catastrophe is, by any reasonable historical comparison, exactly that kind of wall. Uncomfortable, stubborn, real, and, if the pattern of the last century of physics holds, eventually, someday, permeable. Perhaps the resolution arrives through a completed theory of quantum gravity, string theory or loop quantum gravity, or some framework neither has yet imagined, finally telling us with confidence what actually happens to space and time at the Planck scale, and in doing so finally teaching us how to correctly sum the restless energy of every quantum field without running headlong into absurdity. Perhaps it arrives through a genuine detection at some future particle collider, evidence of supersymmetric partners, or some entirely different class of new particle, quietly explaining the cancellation that seemed so elegant on paper decades ago, but has so far eluded every experimental search. Perhaps it arrives through the patient astronomical work already underway right now. Desi and Euclid and the Vera Rubin Observatory slowly, carefully mapping the entire history of cosmic expansion in enough detail to finally reveal whether dark energy is truly constant or genuinely evolving, closing off entire branches of theoretical possibility, one careful measurement at a time. Or perhaps, and this is the possibility that unsettles even seasoned physicists the most, the resolution is not a resolution at all in the traditional sense, but an acceptance that some features of our particular universe, including the precise weight of empty space, simply do not have a deeper derivation waiting to be found. That they are, in the end, nothing more or less than the specific conditions that happen to permit someone, somewhere, eventually, to lie quietly in a dark room and wonder about them. Nobody currently knows which of these futures is waiting for us. What we do know, with complete confidence, sitting here tonight, is that the question itself has never been more alive, more actively pursued, more richly supported by real, ongoing observation than it is at this exact moment in the long history of human curiosity. That is not a small thing to be able to say about the emptiest, quietest, most overlooked corner of physics, the space between things, the nothing that was never really nothing at all. So here is where tonight leaves you, lying in a room that only feels still. The space around you, the space between your fingers, the space stretching out past the walls of this house, past the edge of the solar system, past the last visible galaxy, has never once stopped moving. It never has. Since the earliest fraction of a second after the universe began, it has been quietly boiling, fluctuating, pushing, and it will keep doing exactly that long after every star you can see tonight has gone dark. We do not know why it weighs what it weighs. We know the number our best theory produces is wrong by more zeros than a human mind can honestly hold at once, and we know that somewhere inside that error is sitting one of the last great unopened doors in physics. Not a door we have failed to find, a door we have already found and are still slowly, patiently learning how to open. There is something quietly comforting in that, if you let it settle. The universe has not finished explaining itself, not to us, not to anyone, and you are here, now, awake to the question. in the narrow window of cosmic history when the sky still holds enough evidence to keep asking it. If tonight's journey through the weight of nothing kept you good company, let the channel know by subscribing so the next quiet mystery finds its way to you when it's ready. Until then, let the vacuum hum on without you. Close your eyes. Let the stillness, real or not, carry you the rest of the way down.